Hello everyone. We are now well into our unit, which corresponds to Chapter 2 in the text. And up to this point, we've been kind of rehashing or taking another look at many of the things you were introduced to either in an Algebra 2 course or a pre-calculus course. And specifically, in things involving functions. So we talked about the different types of functions, some of the characteristics of all functions, like what's their domain, what about the range, what are some of the other specific types of characteristics? What about some intercepts? And then you had some very short problem sets on specific types of functions, whether they were the quadratics, rational, radical, and then we can just continue to move on after that. Most of it, as I said, you've at least seen before, but there are a few little types of problems that may be new, the main one being when we look at a reciprocal of a function that's already graphed and how that changes it. It's not as simple as other types of transformations, left, right, up and down, a stretch, compression. This really changes the look of a function. And in order to graph some of these high-level functions, especially rational functions, using the reciprocal idea, it's kind of a long process. We can start with the denominator, and once we get that graphed, we somehow have to flip it and figure out what the reciprocal could look like. So that was probably the newest thing that you might have gained early on in the chapter. We then moved briefly to a technique called partial fractions or partial fraction decomposition. And it was just a way to take a single rational expression and write it as a sum or difference of two other rational expressions, each of those being a simplified version. Now, it's very limited as what it must look like to start in order to use that partial fraction decomposition. So we're just scratching the surface on that method, but at least we have the introduction. What I want to focus on today is kind of the middle to end of this big unit, and that involves absolute value and absolute value functions. So here we go. Absolute value, what is it? Well, we know a lot of things about it. And if I had you here in class, I'd be asking you, what do you remember about it? Most people remember, well, when you graph it, it's a V. That's true if it's a linear absolute value, but it's not true of everything. Many people would say, well, it's always positive. Yes, once you perform the absolute value on any quantity or function, it's positive, which can give us a clue as to what the graph could be. If we have the absolute value of any function, just graph the function without the absolute value, and flip everything that's below the x-axis above the x-axis, and we have an absolute value function. A characteristic that usually comes from that are these sharp turns, or these points. The classic V is one of them, but we could have other types. Now, another way to think of an absolute value function really is a piecewise function depending on the input. So absolute value of x, for example, can be considered either x or negative x. And that fundamental idea leads us to a technique that we can use to solve all sorts of absolute value equations and inequalities. Still another way to think of absolute value, just to be complete. If I gave you a little riddle and told you to put this in mathematical form, and I would say I'm thinking of a number that is 4 units from 3 on a number line. That's what this means. It's a number, 4 units from 3. So that's kind of an elementary way of thinking about absolute value in terms of a number line. But what we want to do is solve some equations. So let's get down to it. Solve this absolute value of x plus 1 equals negative 2x minus 5. Now, many of you already know that, well, a very popular technique is to just let what's inside the absolute value symbol be this value or the opposite of that value. And that's kind of reverse of what we could use here. I could make just this side either x plus 1 or the negative of x plus 1. But the end result is the same. So let's just go ahead and do this. I can either let x plus 1 equal exactly what we have, or I could let the x plus 1 equal the opposite of that. Now, as we solve each one separately, this becomes 3x equals negative 6. That's right, 3x. Subtract 1, negative 6. x equals -2. Here we have x equals -4, and that's it. Now, one thing we'll notice with absolute value equations, and inequalities especially, well, equations, is that we can have these roots or zeros or solutions that really don't work. The fancy word for it is extraneous, for extra. It was very common when working with some quadratics or functions that aren't quadratics to start, but to solve the equation we make them quadratics, which have two solutions, but the original might only have one. In any case, we should check these. If I put a -2 in here, that's not going to happen, because that's going to be -1 on this side. This can't be negative, so I got to throw this out as extraneous. This one, however, will work. Put a -4 there, it becomes a -3, then 3. -4 here would also become 3. So this one checks out. That's our only solution. Now, if you wanted to even take another look at why that's true, we could sketch the graph of both of these. The absolute value of x plus 1 is simply moving 1 back, still a slope of 1. There's my absolute value of x plus 1. We also know what -2x minus 5 looks like. Intercept -5, slope of -2. Eventually it's going to hit, and -4 is a believable one. But it's not going to hit this kind of other part of my function. So, never a bad idea to consider the graph if you're unsure. Plus, the more often you graph something, even with a calculator, I think the deeper understanding you might have, even when you're not allowed to use one. Let's go to our second. Solve this absolute value equation. At first glance, some people would think, well, I got a lot of possibilities. They could both be equal. They could both be negative. This could be negative and that could be positive, or this could be negative and that could be positive. But if you investigate that a little bit further, for example, when they're both positive, or if they're both negative, that's really the same equation. Because you'd have a -1 kind of coefficient or factor on both sides. You can divide by -1 and get rid of that. So it might appear we have 4 different cases, but in reality there's just 2. So let's see what we have here. I'm simply going to write that 3x minus 4 is going to equal 2x plus 3. The other option is 3x minus 4 will be the opposite of 2x plus 3. Now, I could have taken the opposite of this one, equal to 2x plus 3. Again, it doesn't matter. Solve this, I get x equals 7. Solve this, I'm going to get 5x equal 1. So x equals 1/5. Again, we should check them. 7 is 21, that's minus 4. 17, okay, that works. 1/5, 2/5 and 3. Here we get 3/5 minus 4, but we take the absolute value. It's going to be the same thing, right? So, 2 fairly standard absolute value equations. Now, on the second one, I want to show another option. Might not be a good option here, but it is a technique that might serve you well in the future. I could take both of these and square them. And set them equal to each other. Because whether they're positive or negative isn't going to affect once I square them. So if these two are equal, the square of each of them would be equal. And once we square it, we don't have the absolute value symbols, and then we could solve this. Now, as I said, in this case, I'm not sure I'd go there, but if you can maybe anticipate the x squareds canceling or some of the other terms canceling to make it fairly simple, it's not a bad option. Okay, our last one is an inequality. And so this brings up a couple different things. One is we're still dealing with absolute value, so we have to be able to handle the positive and negative version. The other is that it's an inequality. And with an inequality, we tend to think of it as an equation. I know years ago when I taught an honors pre-calc section, I had to search to be able to find problems like this because it wasn't part of the core kind of content of a pre-calc course at that time. But I do know that if I set these equal to each other and then solve those, that's a start. So even if it's in an inequality, I'm still thinking it as an equation. So x squared minus 5x could equal 6, or it's not a 6, there's a 6. X squared minus 5x could equal negative 6. If I solve each of these, x squared minus 5x minus 6 equals 0. That does factor. We got minus 6 plus 1. So x is negative 1. X equals 6. This case, same idea. Here again, it factors. We pick some nice numbers, so everything factors beautifully. We're going to have minus 3 and minus 2. So x equals 3 and x equals 2. So I found a lot of values where these are equal to each other, but I want this to be less than. Now there are various options about how we want to go about this. This technique probably isn't even mentioned in the text at this time, but I want to point it out because I think it's a nice technique. And sometimes people refer to it simply as interval testing. And it's all based on the premise that as long as this is a nice continuous function on both sides, which they are, or even if I change it, if I know that two things are equal at 2 points, then in between all of the points, it's either greater than or less than. It's really a trichotomy of numbers. You have two numbers that are either the same, one's bigger than the other, or one's smaller than the other. That's it, the only options. So here's where I have them being equal to each other. So I'm just going to make a simple number line, and I'm going to plot those points on the number line. They don't have to be equally spaced, but there they are. And then I'm going to test an interval. Again, remembering that as long as it's true for 1 point on the interval, it's always true for every number in that interval. So I'll start with an easy one like right here, 4. If I put a 4 into the equation, let's see what happens. Okay, I could put it into one of these other equations, but that's not the point. 16 minus 20 is negative 4, absolute value is 4. 4 is less than 6, it's true. You could say true, you could say yes, put a check, I don't care. But somehow you have to indicate all those numbers work. We could pick like 2.5. If I put a 2.5 in here, 6.25 minus 12.5, negative 6.25, that's a big no. I could put a 7 in, 49 minus 35, definitely a no. I could put a 0 in, I like 0. 0's, yeah, that's true. And we start to assume that we're going to have alternating yes, no, but don't assume it. And then lastly, you put like a negative 2 in, so 4 plus, no, that didn't work either. So what we have here is x has to be less than 2 or greater than negative 1, or x is less than 6, greater than 3. Now, of course, if you want to use interval notation, there's no issue with that. But these are my x values. And you can spot check them if you need to, but you really don't need to, because you found out where they're equal as long as you're comfortable with that. So that interval testing is nice. I think there's another one maybe described in the text that you might want to look at. You can use a lot of ands and ors here and kind of figure out if this is and, it's the or. But as I said, I think the interval testing, when you have a lot of these options, a lot of these intervals, it can be very helpful. It's also going to be a test that we'll make quite a bit of use of when we get into our calculus topic. One final comment for the day is if this happens, one of these inequalities happens to be maybe a rational inequality, like I can think of 1 over 2x minus 1, me squeeze that in here. Sorry about this, but let's say we just want it to be less than 1 or some number. Again, we can do the same thing. We can solve it, find out when they're equal. And then there's one other point we have to put on the number line. And that would be any restriction in the domain. Here we had nice continuous quadratics, so there weren't any restrictions in the domain, so we just had the solutions. But in this case, in addition to the solutions, we would want to put 1/2 on your number line. Reason being is that would typically indicate graphically an asymptote, and things can change in an asymptote without passing through the asymptote. So, one little hint. Other than that, I think hopefully that's enough. But what we're trying to do is solve some equations that involve absolute value, solve some inequalities that involve absolute value. And this pretty much should take us through about section 2, H and I. The last one, J, is about a piecewise function. And once again, I'm kind of relying on your previous knowledge to be able to look at those problems in the problem set and be comfortable with them. If not, you bring your questions to class or when we meet online, and we can take care of those. So good luck with the problem sets from Chapter 2 up to this point. As always, if you have any questions or concerns, contact me and we'll work something out. You have a good day.